So this is an example in this question of heat conduction. The heat conduction is the heat released by the melting ice. So Q is equal to Mi times LF, where LF is the latent heat constant. Mi is the mass of the ice. Okay. So the area through which the heat is conducted is the total area of the 6 surfaces of the box. And we were told that the dimensions of the box are 25 by 35 by 55 centimeters. Okay. So the length of the conducting material is the thickness of the styrofoam L, which is 1.5 times 10 to the minus 2 meters, or 0.015 meters. So we assume that all of the heat conducting into the box goes into melting the ice and none into the raising the temperature outside the box. So the time can be calculated by equation 14-5. So we'll write that out here, which is equal to Q over T, which is equal to constant K times the area in question times the change in temperature, delta T, which we have as 34 degrees Celsius, divided by the thickness, L. Therefore, solving this equation for T, we have this is going to be equal to the mass of the ice times the latent heat, which is just subbing that value in for Q, divided by K times the area times the change in temperature. But we're only considering the inside surface, not the outside surface. So this can all be multiplied by 1/2 because we're only considering half of the total surface, just the inside. Okay, so therefore, T is equal to, in the numerator, we still have Mi times L sub F divided by, well, we'll just pull that 2 out front, multiplied by the constant K. But actually, this 2 is going to end up being a 4 because it's going to be 2 times 2. And we'll explain where that other 2 comes from here in just a second. Times K. And then multiplied, well, now we have to find the area. But the area is going to be the total of the area of each of the 6 sides that make up the box. But since there are 6 sides that make up the box and 3 of them are actually identical, each 3 of those are going to be multiplied by 2. So that's why that 2 got pulled out front. So we're going to have one of the sides, which was 0.25 meters times 0.35 meters. So that would have units of meters squared, plus 0.25 meters times 0.55 meters. And of course, meters times meters is going to give us, again, units of meters squared. So that's the area of the other side. And again, each of these would have been multiplied by 2 because there's 2 of these sides. So there's 2 sides that have a dimension of 0.25 times 0.35, 2 sides that have the dimension of 0.25 times 0.55, and we just pulled that 2 out front. So it's going to be meters squared plus the last one. I'm going to extend this here. Oh, I actually forgot the length here. So this is T over L, so there should be an L here. And there should be an L here for the thickness. Okay? And then the last one is for the area. The last side is 0.35 meters times 0.55 meters. So that's, again, going to give us units of meters squared. And then all of that, because that's the area, is multiplied by the change in temperature, delta T. And let's go ahead and extend this out a little bit because this is indicating what's in the numerator and what's in the denominator. So plugging all these values into this expression, we find that T is equal to 3.1 times 10 to the 4. And the units here are seconds. And we can box that in as our solution to the question.